So let's have a look at equilibrium. Equilibrium is a condition where forces and moments, we'll get into those later, are balanced on an object so it doesn't accelerate, okay? Which is a pretty important thing sometimes. You know, if you're doing things that are supposed to stay still, you want them to stay still. You want the forces to be balanced on them, okay? All right, so if the acceleration is 0, if we go back to that basic equation from Newton that F equals ma, if the acceleration is 0 for equilibrium, that means the sum of forces is 0. All right. So I'm on page 240 here. So if I have an object and I'm pushing to the right on it with 40 pounds, and I have some sort of support on there, and I know that things in equilibrium, if I have some sort of support here, what I can figure out is the reaction of the support on that object would have to be 40 pounds to hold it in equilibrium, okay? If I have a 40-pound push to the right and I've got 10 pounds pushing to the left, I can know this second force would have to be 30 pounds to the left to hold the object in equilibrium. If I have a weight of a bridge, which is 6 tons, I know the net forces on the 2 footings that are holding the bridge up would be 6 tons, okay? That's basic equilibrium there. So to analyze the forces acting on objects, we draw up what are called Freebody Diagrams, which is kind of a funny word. I like to call them force diagrams because it makes more sense. Free body means an object that you're just looking at the object as though it's in space, and you're looking at all, and then it's a diagram that you draw up. So that's where that term comes from. It's very commonly used, FBD, sometimes just to abbreviate it. Okay. So these are just force diagrams, is how I think of them. You decide what you want the object to be, which is the body, draw a boundary around it, and then draw in the forces acting on the body. There's 2 possibilities for these forces. One are contact forces, which are caused by physical contact. The other are body forces, which are caused by force fields. Now, if you're in physics, you probably encounter lots of force fields, gravity and electromagnetism and things like that. But here in statics, we're going to stick with more everyday engineering stuff. We're just going to deal with gravity here. And that's the only body force we have, which is a force field. Okay? So we're going to look in particular for contact forces, things that are pushing or pulling on the object. Right? Now there's some special types of forces that we want to cover. So let's have a look at these. The first one is a cable, a chain, a rope, something like that. Now the first thing with a cable is all you can do with a cable is pull. Okay? Because a cable is not rigid. What happens if I try and push with a cable? Not much, huh? Okay? So a cable can only pull. Now, the other thing about a cable, though, is the angle of the cable is also the angle of the force. If I want to pull this weight up, the cable is vertical if I'm pulling up with it. If I can't pull up with an angled cable, right? I can pull that way, but if I try and pull up with an angled cable, what happens to the angle of the cable very quickly? It turns vertical, right? And to contrast that with a rigid object, I can take an object that has rigidity and I can push that cup up, the weight up, with a horizontal object. See, I can't do that with a cable. So a cable, if you know the angle of the cable, you also know the angle of the force. Okay? Good with that? So if you know the angle of the cable, it's also the angle of the force. You also know that the cable can only pull. Okay. Okay, a pulley, there's another thing you might run into. Right now, what a pulley does is it changes the direction of a cable. Now, if we have something that's in static equilibrium, if something's in static equilibrium, the forces on both sides of the pulley are the same. I've got this small here. Here we go. There we go. All right. So if that thing weighs 3 pounds, the force in the cable on this side is 3 pounds. And if it's in static equilibrium, it's also the force on the other side. So if you've got a pulley and a cable is in, and you've got a weight, and the pulley is in static equilibrium, and the weight is, the tension everywhere in that cable will be the same. All the pulley does is change the direction. We assume normally that the pulley is frictionless. So there's a little sketch of that. So if this thing weighs 160 newtons, and we want to draw a free body diagram of the pulley, that cable will be pulling in both directions with 160 newtons. That way it won't move. It's in static equilibrium. Okay. So that's the assumption that we make with pulleys. The last thing here is a spring. Okay, now there's different types of springs that are manufactured to do different things. We're going to deal in this class primarily with linear springs, which means they have a constant cylindrical wrap on them. Okay, so they're wrapped in a cylindrical shape, and they have the same number of lines per inch. What you then have with a spring is the force in the spring is equal to what's called the spring constant, K, times the amount of stretch or compression in the spring. So if K is 60 newtons per meter, and you know that the amount of stretch in the spring is 0.4 meters, you can find the force in the spring, 24 newtons. Okay? So K is the spring constant, which is the amount of force per unit length. Okay? S is the amount of stretch or compression. So S is not the length of the spring, it's the amount of stretch in the spring or compression in the spring. Now, that's the relationship for a linear spring, which seems to be the popular kind of springs that you have in statics. You can have nonlinear springs like that are made to have a different force for the force to change as you kind of work your way through the spring. Okay, you could also do that by changing the wraps. I think some of the old shock absorber springs, when they had shock absorbers on cars, were nonlinear. I think they kind of got stiffer as you got closer to bottoming out the car. I think that's how that worked. Okay, but we're going to stick with linear springs. All right, what do we got? All right, let's have a quick look at this. So let's have a look at how we could solve a two-dimensional equilibrium problem. Now this is a simple form of equilibrium. We're just going to look at a point being in equilibrium. We're not going to look at a full, what I call a rigid body, a full object with dimensions and all that sort of thing. We're just going to look at a ring being in equilibrium there. Okay, so let's have a look. Now let's figure out what page we're on here. About 240 maybe, is that it? 244. Okay, thanks, so 244. Let's say with that ring's in equilibrium, okay? And it's held in equilibrium by those two masses, B and C, and by the spring on the bottom. Say the mass of the ring is 4 kilograms. The unstretched length of the spring is 0.8 meters. And the spring constant, K, is 450 newtons per meter. And the pulleys are frictionless. Let's find the mass of B and C. Okay. Now that's a little, it's not horribly complicated, but there's a few things going on in that system. The key to figuring this thing out is that we want to find the forces in the cables. The cable that goes from A to B and the cable that goes from A around to C. If we can find those forces, we can figure out the masses. Okay? So what we need to do is to draw a free body diagram, which is a force diagram of something that will get us the forces in the cables. And what do you suppose we'll draw a free body diagram of if we want to find the forces in both of those cables at once? A. I think A is the answer, yes. Okay. So when I want to find a free body diagram of A, what I do is I draw a boundary around it. Anything I cut through is what's called a contact force. So I'm cutting through three things, the spring and each of the cables. They are now contact forces. So I have to model those with forces on my ring. And that's where the term free body comes from. I'm cutting the ring free of all its constraints, and I'm going to model those constraints as forces. All right? So how about taking 5 minutes or a couple minutes, let's do a couple minutes, and come up with your best free body diagram you can of the ring. What's happening to the ring right now from its perspective? What's going on? So just a couple minutes there. Yeah, you're going to have to figure out the stretch and multiply it by k. Yeah, just start with putting arrows on the ring, and then you can find that spring force, and there's also the weight of the ring too, so that goes in there as well. Those cables are going to pull, right? And the spring's going to do what? Push or pull? Pull down, right? Because we're looking from the perspective of the ring. We're looking at what happens to the ring, okay? And all those cables can do is pull. Yeah, question there.
Is the bottom, that bottom arrow, is that representing its weight?
It's two. Actually, there's two arrows there. When you get the whole thing, there's the weight, and then there's also the spring force too. So there's, you could put them as one. I'd probably put them as two.
So the spring force is also being applied down.
Down, yeah.
It's compressing.
Well, the spring's intention, it's stretching, so it's pulling down on the ring.
It's not okay. So it's not. There's no force pushing up against the ring.
No, there's a force pulling up on the spring. But the spring is pulling down on the ring. You have to keep track of which object you're looking at.
Okay. So in that case, it's absorbing.
Yeah, it's kind of absorbing the spring is what it's doing. Yeah. Okay. All right. So I get to something like that. So the weight would be the 4 kilograms times gravity, which is metric, 9.81 meters per second squared. That's 39.2. That would go down. The spring stretch is 1.42 minus the unstretched length of 0.8. It's 0.62 meters, 450 newtons per meter, 279 newtons down. And then the forces in the cable are unknown.
We don't have a way of being data.
Yeah, we're finding those. That we're going to find the forces in the cable to hold the thing in equilibrium. From that, we'll get the weights of B and C. From that, we'll back into the masses. So everybody good with that free body diagram? Okay. So those are the forces acting on the ring. And you know, that question about the spring direction is good because you're taking it from the perspective of the ring. The ring is being pulled down. Okay. All right. So now we've got two unknowns. I don't know what those cable forces are, but the good news is I've got two directions. See, forces are vectors. I've got an x direction and a y direction. So I have two equations I can generate, one based on x and the other based on y. Okay. So I have two unknowns, so I should be able to solve this thing out. So we good on the free body diagram? We good? All right, so what I'm going to do here is generate a sum of fx equation, because what I have here is sum of f as a vector is equal to 0. Well, what that means is sum of fx is 0 as a scalar, and sum of fy is 0. So I have those two equations that I can use to analyze this, because I'm in two dimensions. Okay, so I can do some trig here and work through that. All right, so I'm going to solve the two equations and the two unknowns. So I need to generate force equations. Now, what I want to do here, I'm going to do a substitution to solve this. Now, I'm just doing this, you know, if you have a solver on your calculator, you can always use that on homework. You can't use a programmable calculator on a test, but on homework, you know how to use those things. You can solve simultaneous equations if you like. But let's see how we would do this kind of old school, okay? So what we're going to do then is we're going to start with sum of fx equals 0, okay? I'm going to do that on purpose because it's the simplest equation. It doesn't include the spring force or the weight. So if I sum forces in the x direction, what I'll get is a nice simple proportion between FB and FC. I can then substitute it into my sum of Fy equation. So I'm looking ahead at that and I'm saying, well, I'm going to do a substitution to solve this thing, and sum of Fx would be a good way to start because that way I can relate FB to FC directly using a bit of trigonometry. Then I can substitute it into the sum of Fy equation. That's what I'm doing there. Okay? So that's what I'm trying to accomplish here. So I'll go sum of fx and set it equal to 0. Okay. And that's just going to involve a little bit of trigonometry. So there's my sum of fx equation for that. See, what I've got is I've got the ring, and I have these two forces at angles. I've got a 60-degree angle for the unknown FB, and then I've got a 20-degree angle for the unknown FC. I have the other two forces, the weight and the spring, but they're in the y direction. I don't worry about those with my sum of fx equation. So what I can do is work through that sum of fx equation and get a nice simple FB equals 1.88 FC. That gets me a nice simple proportional relationship. Okay, so that gets me that. Now I can then set up the more complex sum of Fy equation and I can plug that in. Okay, and that way I can solve my two equations and my two unknowns pretty readily. Okay. So I just looked ahead in that and did the simpler one first. Then I can do the sum of Fy equation. And what I've got for sum of Fy is I've got the sine of 60 FB, because that one's going up, so that'll be a positive 60 degrees, or sine of 60 FB is positive. And then I've got the sine of 20 for this one, FC, and then I have the weight of the ring down, 39.2 newtons. And I've got the spring force down. Okay. So I can generate a little bit more complex sum of Fy. Okay. So that'll be sine of 60 FB up, that's positive. And then I've got sine of 20 FC up, positive, minus the weight and minus the spring force. So when I get that sorted out, I get the 279 and the 39.2. That gets me 318.2. That's, I put that on the left side of the equation. It's positive when I take it over there. And when I do the trig, I get 0.866 FB plus 0.342 FC. And then I've got a substitution ready to go that I can plug right in there. I've got this. So I can put that in for FB now. And then I'll solve for FC. Okay. Okay. So I'll go ahead and do that, and I'll get 318.2 is equal to 0.866, and then I'll plug in this bit for FC. It's 1.88 FC. Well, that goes in for FB, I should say, and then I got 0.342 FC. And I can solve for FC and then come back and get FB. That's the idea here, okay? So I plug that in, I get 318.2 is 1.97 FC. So FC is 162. I know that FB is 1.88 times that, so FB is 304. Those are forces in the cables. So what I need to do then is realize to get masses. Those are weights of those. Those are the weights of B and C is what they are, because they're the forces in the cables. So what I can do then is take the weights, those weights, and divide them by gravity, and I'll get the masses of the two of B and C. Okay. Okay. Usually do Friday, won't they? Right? Now we'll cover them Friday, but we'll push them back to Friday. That'll be okay. 24th. So ways out. There we go. Okay. So we'll make those due on Friday. Not this Friday. A week from this Friday. Next week. Yeah. Yeah, I'll move the stuff, the 5 problems we did to Wednesday, and then I'll move, this stuff will be due next week on Friday. Yeah, okay? And we'll cover these. All right? So we good? Great. I'm just gonna take a minute, shut this recording down. I'll get back to